Friends, we should study today sub-synchronous oscillations in the power system. In the analysis of power system dynamics, so far we have considered the rotor of the turbine generator system as a single mass system. Such a representation accounts for the system mode of oscillations. The frequency of this mode of oscillation is in the range 0.2 to 2 hertz in the system. In reality, the turbine generator rotor is a very complex in structure mechanically. It has several masses mounted on the same shaft. It has high pressure turbine section, intermediate pressure turbine section, low pressure turbine sections, generator and exciter mounted on the same shaft. And if such a turbine generator rotor, when it is disturbed or perturbed, torsional oscillations are produced. And these torsional oscillations in the sub-synchronous frequency range in certain conditions may interact with the electrical system, and such interaction may be an adverse interaction. In view of this, it is necessary to study the sub-synchronous oscillations in detail. The problems related to torsional oscillations are torsional interaction with power system controls, sub-synchronous resonance and torsional fatigue due to network switching. We shall study all these aspects while discussing the torsional oscillations or sub-synchronous oscillations in the system. Before we address these specific problems, the first step in the study of sub-synchronous oscillations is to develop the detailed model of the turbine generator shaft system. Now, in order to develop the dynamic model of the turbine generator shaft system, we consider a tandem compound steam turbine, which consists of high pressure section, intermediate pressure section and low pressure section B and low pressure section A. All these 4 steam turbine sections are mounted on the same shaft. In addition to this, the generator is also mounted on the same shaft, generator rotor. Here we will consider the static excitation system, and in case the system comprises of a rotating exciter, then one more mass will have to be represented on the same shaft. Now, here in order to develop the dynamic model of the shaft system or turbine generator shaft system, we will consider that the torques which are developed in the various turbine sections are represented as THP, represent the torque developed in the high pressure section, TIP is the torque developed in the intermediate pressure section, TLPB is the torque developed in the low pressure B section, and TLPA is the torque developed in the low pressure A section, and the air gap torque developed in the generator is represented by TE. Further the shaft connecting the high pressure and intermediate section, similarly the intermediate pressure and low pressure sections, the shafts have finite stiffness coefficient. The stiffness coefficients will be represented by the symbol K45 joining the high pressure and intermediate pressure section. Similarly, K34 is the stiffness coefficient of the shaft connecting intermediate pressure and LPB, and similarly the K23 and K12 are the stiffness coefficients of the shaft sections connecting LPB and LPA and generator sections. While we develop the dynamic model of the system, we will assume that the torque developed in these various turbine sections are constant. Now, this assumption is particularly used for developing the small perturbation dynamic model of the system. Now, here each section, that is the generator, LPA, LPB, intermediate pressure and high pressure section, they have their inertia constants. We will represent the inertia constant of generator by the symbol H1, inertia constant of the generator, that is the not generator but steam turbine section LPA by H2, and similarly the inertia constant of LPB, IP and HP sections. Further, we will assume that there is some damping associated with the oscillation of these masses. Now, here in this model the various turbine sections and generator are represented by lumped mass. The dampings associated with these 5 different masses are represented as D1, D2, D3, D4 and D5. Now, let us understand what causes damping in the turbine generator shaft system. Now, when the blades of the steam turbine are rotating in the steam which is flowing, right. Therefore, in this process there exists some viscous damping, right, and similarly the damping is also produced when the generator rotor is rotating. Therefore, the generator rotor also produce some damping because of the damper windings and other phenomena which exist in the system. Similarly, when this system is connected to the electrical network, then this electrical network also produces some damping. Now, damping is also produced by the mechanical hysteresis of the shafts connecting the various turbine sections. Therefore, there exists some damping in the system. However, the damping produced due to these various phenomena is very small in magnitude. We will develop the dynamic model of the system assuming the certain finite value of the dampings associated with the generator and steam turbine sections. Now, let us just understand the meaning of the stiffness coefficient. The stiffness coefficient is represented by the symbol K, and when we represent the stiffness coefficient of the particular shaft section, we will add additional subscripts. The torsional stiffness defines the relationship between the torque transmitted and the angular twist between the two ends of the shaft. This is very important, that when the torque is transmitted by the shaft, right, then there is a relationship between the torque transmitted and the angular twist between the two ends of the shaft, and the relationship is represented by this equation T equal to K theta, where theta is the angular twist and K is the stiffness coefficient, and torque T stands for the torque transmitted by the shaft. Now, in order to develop the dynamic model of the system, let us consider consider the generator and LPA turbine section in detail. On the rotor of the generator, a torque Te, which is the air gap torque, is acting. Now, this torque acts in a direction opposite to the direction in which the rotor is rotating. Now, this generator rotor is connected to the turbine section LPA. The shaft connecting the turbine section LPA and generator has a stiffness coefficient K12. The driving torque produced by the shaft is represented as T12 acting in the direction of rotation. Therefore, when we look actually at the dynamics of the generator rotor, we have two torques acting on the rotor. One is the torque transmitted by the shaft, that is T12, another is the air gap torque Te. In addition to this, there is some damping torque acting on the generator rotor. Now, here the position of the rotor will be represented with respect to the synchronously rotating reference frame. This phasor represents the synchronously rotating reference frame. The speed of this is omega O. The generator rotor rotates at a speed omega 1 and its axis is displaced with respect to the synchronously rotating reference frame by an angle delta 1. Similarly, when I talk about the turbine section LPA, then the position of the rotor with respect to the synchronously rotating reference frame is denoted by an angle delta 2 and the speed is omega 2. Under steady state conditions, the omega naught, omega 1 and omega 2, they are all equal. However, there is a finite value of the delta 1, delta 2 and so on. Now, in order to develop or in order to write the equation of motion for the generator, let us write down the accelerating torque acting on the generator rotor. The accelerating torque acting on generator rotor is equal to T12 minus Te. Now, this T12 can be expressed as K12 into delta 2 minus delta 1 minus T. Therefore, the accelerating torque which is acting on the generator rotor is this. Now, when we consider the damping of the generator rotor, then the damping torque which acts on the system will be acting in the direction opposite to the accelerating torque. Therefore, the net accelerating torque will be this K12 into delta 2 minus delta 1 minus T minus d1 delta omega 1. The equations of motion of the generator rotor now can be written as 2 times H1 d by dt of delta omega 1 equal to Ta, with accelerating torque, is equal to T12 into delta 2 minus delta 1 minus T minus d1 times delta omega 1, right. That this is the net accelerating torque which is acting on the generator rotor. Now, in this equation, the speed deviation is represented in per unit. The equation d by dt of delta 1 is equal to omega naught into delta omega 1. Therefore, these two equations represents the equation of motion of the generator rotor. These are the two first order differential equations. Now, let us consider the steam turbine section LPA. Now, when I look at this steam turbine section LPA, then we can clearly see that the accelerating torque acting on the steam turbine section LPA can be written as that the driving torque is T23 plus the torque developed in the steam turbine section, that is T23 plus TLPA is the driving torque, while the braking torque is T12, and therefore, the net accelerating torque will be T23 plus TLPA minus T12 minus d2 delta omega 2, and therefore, the equation of motion for the LPA rotor, that is the steam turbine rotor represented as LPA, can be written as 2 times H2 d by dt of delta omega 2 equal to TLPA torque developed in the steam turbine section plus K23 delta 3 minus delta 2, that is this is your T23 minus K12 into delta 2 minus delta 1. Therefore, this quantity is T12 and multiplied by d2 into delta omega 2. This is the damping torque. Therefore, the net torque acting or net accelerating torque is TLPA plus T23 minus T12 minus d2 delta omega 2. The second equation, the differential equation for this LPA rotor is d by dt of delta 2 equal to omega naught into delta omega 2. Similarly, we can write down the equations of motion for LPB, IP and HP sections. The equations of motion for LPB rotor are 2 times H3 d by dt of delta omega 3 equal to TLPB plus it will be T34, which is equal to K34 into delta 4 minus delta 3 minus T23, which is written as K23 into delta 3 minus delta 2 minus D3 delta omega 3, and the next equation is d by dt of delta 3 equal to omega naught into delta omega 3. The equations of motion for IP turbine section are written in the same way as we have done for LPB and LPA sections. There is 2 times H4 d by dt of delta omega 4 equal to TIP plus K4 5 delta 5 minus delta 4 minus K34 into delta 4 minus delta 3 minus D4 delta omega 4, and d by dt of delta 4 equal to omega naught delta omega 4. Our next step is to write down the equation for the last turbine section, that is the high pressure turbine section. Now, when we look at the high pressure turbine section, then there is no shaft on the left of the high pressure turbine section, and therefore, the net accelerating torque acting on the high pressure turbine rotor is THP, the torque which is developed in the turbine section, minus K45 minus D4 D5 into delta omega 5, and therefore, the equation of motion is written here as 2 times H5 d by dt of delta omega 5, that is equal to THP that is the torque developed in the high pressure turbine section, minus K 4 phi into delta phi minus delta 4 minus d phi delta omega phi, and d by dt of delta phi equal to omega naught delta omega phi. Now, for this 5 mass turbine generator shaft, we have written 10 first order differential equations. Now, these differential equations are non-linear differential equations. The equations are non-linear because the air gap torque T e is non-linearly related to the angular positions of the generator. Now, we will attempt a simple problem. The problem is like this: we consider the same 5 mass system, we will consider this same 5 mass system, and we will assume that the power torque developed under steady state condition in the high pressure, intermediate pressure, LPB, LPA have certain fixed ratios. Now, for this particular problem, our interest will be to find out that if the generator is delivering certain amount of power, right, then how much is the power which is transferred through each of the shaft sections. That is the power or the torque transmitted by each of the shaft sections which are connecting the various turbine sections and the generator. We will also find out that how much is the total angular twist which is created from generator to high pressure turbine section. Now, to illustrate this, we will consider that this system has the various stiffness coefficients. K 12 is given as 37.25, K 23 is 31.31, K 34 is 27.66, K 45 is 17.78. Now, these coefficients are expressed in per unit torque per electrical radian or per radian, right. Further, we will assume that the power output from the generator is 0.9 per unit, and in per unit system the air gap torque T is also equal to 0.9 per unit. Now, to solve this problem, we need one more information, and that information is that what is the fraction of torque which is produced in high pressure, intermediate pressure, low pressure and A and B sections. We will assume here in this say that the fractions of the torque which are produced in the HP is 0.28, while the fraction of torque which is developed in T, the intermediate pressure, this TIP, is equal to TLPB also equal to TLPA equal to 0.24. So, that when you add these fractions, the sum is 1. Now, when the torque which is produced in the by the generator is represented as T e and its value is 0.9 per unit, then the actual torque which is produced by HP, IP and LP sections can be obtained by multiplying all these coefficients or these fractions by 0.9. Therefore, we can say that the THP produced is 0.28 into 0.9. Similarly, TIP equal to TLPB equal to TLPA equal to 0.24 into 0.9. What is this value? 0.216. And what is this value? 0.252. The meaning here is that when the generator is delivering 0.9 per unit power, right, the torques produced in the IP, LPB, LPA section is 0.216 and torque produced in HP section is 0.252. Now, our interest is to find out how much is the torque transmitted through each of the shaft sections. Then I want to know what is T12, what is T23, what is T34 and what is T45. Now, to answer this, what we have to do is that we make use of our definition for stiffness coefficient. Our stiffness coefficient is that the torque transmitted is equal to the angular twist into stiffness coefficient. Therefore, the angular twist of the shaft section connecting the turbine section LPA and generator is delta 2 minus delta 1, and therefore, this delta 2 minus delta 1 is equal to T12 upon K12. Now, the T12 under steady state condition is equal to TE, okay, because under steady state condition the net accelerating torque is 0. Therefore, this angular twist delta 2 minus delta 1 can be obtained as TE divided by K12, and when you substitute the value of TE equal to 0.9 and value of K12 as 37.25, we will get delta 2 minus delta 1 as 0.0246 radian. Now, the torque transmitted through the shaft section connecting the turbine section LPB to LPA is T12 minus LPA, TLPA. Now, T12 is 0.9 and the torque developed in the turbine section LPA is 0.216. This is the torque which is transmitted, and therefore, the angular twist is delta 3 minus delta 2 of the second shaft section, that is T23 divided by K23. When you substitute the values of T23 and K23, you will get the angular twist as 0.02185 radians. Similarly, one can find out the angular twist delta 4 minus delta 3, delta 5 minus delta 4, and these come out to be like this. And the net angular twist or angular twist of the high pressure section and the generator, or you can say the net angular difference between the axis of the generator rotor and the axis of the high pressure steam turbine comes out to be 4.42 electrical degrees. Therefore, when you can easily understand here that when the steam turbine is delivering certain power, that there exists a certain net twist in the shafts, and the net twist is given by this formula delta 5 minus delta 1 here. And you can see here actually that the angular twist is small, okay. When it is delivering 90% of the rated power, its twist is hardly of the order of few electrical degrees. Now, the next step will be to develop the linear dynamic model of the system. Now, in order to develop the linear dynamic model of the system, what we do is that we linearize these differential equations around the nominal operating conditions. Further, while doing this linearization, we will assume that the torque developed in the various turbine sections are constant, right. So, that we can write down now that under small perturbation, when the system is perturbed, the Te, the electrical torque or the air gap torque, is equal to Teo plus delta Te. Similarly, since we have assumed this, the torque developed in various turbine sections constant, right. Therefore, the T HP is equal to T HPO, there is no change. Similarly, T IP will be equal to the T IPO. Now, this O stands for, or 0 stands for steady state value of the torques, and similarly we can write down that T LPB equal to T LPBO and T LPA equal to T LPA. Now, these angular positions will represent the angular positions, like said, angular position under the dynamic condition as delta 1 equal to delta 1 O plus delta delta 1. Similarly, delta 2 will be written as delta 2 O plus delta 2, and so on. We can write down the delta 5 as delta 5 O plus delta 5. Similarly, when you talk about the speed, right, now under steady state conditions omega 1, omega 2, omega 5 are equal to omega naught, okay, and when the system is perturbed, the deviation in the speeds is delta omega 1, delta omega 2 and delta omega 5. Now, using these small perturbations around the operating condition, we can write down the dynamic model of the system around the operating condition. Now, suppose I consider this equation, this is the equation for motion of the generator rotor. Now, here when you substitute delta 2 equal to delta 2 O plus delta delta, delta 1 equal to delta 1 O plus delta delta, Te as Teo plus delta Te, and this term remains same. Now, with this, when you substitute the quantities, we can write down the equation in this form: 2 times H 1 d delta omega 1 by dt, or d by dt of delta omega 1 equal to the torque which is acting here on this is the accelerating torque which is acting on this is T 12. Okay. Now, this T 12 can be written as is K 12 into delta 2 O plus delta minus delta 1 O minus delta, this is delta 2 1, okay, minus Teo minus delta Te minus d1 delta omega 1. Now, remember that when we had written actually the derivative of speed, d by dt of delta omega 1 is same as d by dt of omega 1. Okay. Now, in this equation under steady state condition, K 12 delta 2 O minus delta 1 O minus Teo equal to is under steady state condition. Therefore, for considering this small perturbation around the steady operating condition, around nominal operating condition, we can write down the linear differential equation as 2 times H 1 d delta omega 1 by dt, that is d by dt of delta omega 1 equal to k 1 2 delta 2 minus delta 1 minus delta T e minus d 1 omega 1. Our second equation, when you write down delta 1 equal to delta 1 O plus delta 1, the linear equation will come out to be d by dt of delta 1 equal to delta omega 1 into. Therefore, these two equations are the linear differential equations. Now, here this torque delta T e is expressed in terms of the deviations of these angles delta 2, delta 1 and so on. It is a function of the deviation of the angular positions of the various rotors. Okay. Therefore, these two equations represents the linear differential equations. Similarly, we can write down or linearize the differential equations associated with the turbine section LPA, turbine section LPB, turbine section intermediate parameter IP and turbine section HP. That is, all the 10 differential equations can be linearized, and once you linearize these equations, we will get the dynamic model of the system in the form x dot equal to A x. That is, we can write down the dynamic model of the complete system in the form x dot equal to A x, where x is the state vector written as delta omega 1, delta 1, delta omega 2, delta 2, delta omega 3, delta 3, delta omega 4, delta 4, delta omega 5, delta 5 transpose. That is, x is a vector comprising of these 10 state variables. Now, once we have obtained the linear dynamic model of the system, we can further study the behavior of the torsional oscillations, or we can study the oscillations of the turbine generator shaft. Now, to study the behavior of this system, first step is to find out Eigen values of the system, and these Eigen values will give you natural frequencies of the shaft system. That is, when we obtain Eigen values, what we will get is, we will get the natural frequencies of the shaft system. Now, the system matrix A is a 10 by 10 matrix, and the elements of this matrix depend upon the damping constants, inertia constants, the stiffness coefficients and the synchronizing torque coefficient. Okay. Now, to understand the behavior of the or dynamic behavior of the turbine generator shaft system, let us take an example. We consider here the same 5 mass system, and we represent these masses as 1, 2, 3, 4 and 5. The inertia constant of HP section is 0.124, inertia constant of IP is 0.232, LP is 1.155 and LPA is 1.192 and generator is 0.855. That is, these are the different values of the inertia constants of the 5 masses. The stiffness coefficient of the shafts connecting the various masses are represented as 21.8, 48.4, 75.6 and 62.3. That is, in this diagram what I have shown is that these are the inertia constant of the 5 masses and these are the stiffness coefficients. Further, we assume that the synchronizing torque coefficient Ks is 1.98, right, and this Ks depends upon the operating condition. Okay. Now, the operating condition which we have considered is that the system is delivering 90% power. Okay. Now, for this system we develop the dynamic model and write down the A matrix or determine the A matrix of the system. Now, in order to simplify our understanding, we neglect here the damping coefficients associated with the system. Right. When you neglect the damping coefficients and we obtain the eigenvalues of the system matrix, the eigenvalues, this system matrix A which I have just now shown is a real matrix, right, and since we have assumed the damping of associated with these masses as negligible, and with this assumption the eigenvalues come out to be all complex conjugate and the real part is 0. Now, for these eigenvalues we can find out the associated natural frequency of oscillation. Now, for this first eigenvalue whose imaginary part is 10.12, the associated natural frequency is 1.671 hertz, and similarly the frequency associated of this second eigenvalue is 16.37, for the third eigenvalue is 24.123, and next is 30.25 and next is 43.996 hertz. Even these are the 5 natural frequencies associated with the turbine generator system. That is, whenever this turbine generator is perturbed, right, then the torsional oscillations are produced and the torsional frequencies are given like this. That is, you can see here that we have for this 5 mass system these 5 different frequencies. The frequency 1.671 can be considered to be the system frequency, where the entire turbine generator mass oscillates with respect to the system, while other 4 frequencies are associated with the different torsional modes of oscillations. Now, to further understand the behavior or dynamic behavior of the system, we analyze the dynamic model of the system further. That is, for each of the eigenvalues we obtain the eigenvector, and we can easily understand the meaning of the eigenvectors. We all know what we stand for eigenvector. That is, for each eigenvalue there exists an eigenvector, and we can understand what the eigenvector stands for. That is, for any eigenvalue lambda I, the column vector phi I which satisfies this equation A phi I equal to lambda I phi I is called the right eigenvector of the matrix A. Now, this phi I is associated with eigenvalue lambda I. If I put I equal to 1, I will get eigenvector 1. If I put I equal to 2, I will get eigenvector corresponding to eigenvalue lambda 2, and so on. Now, this eigenvector will have the same dimension as the dimension of state vector. Okay. The eigenvector phi I corresponding to lambda I gives mode shape. We have to understand this, very important, this is very important term, gives mode shape, that is the relative activity of a state variable in a given mode. Okay. Now, to understand this, what we will do is that we will find out the eigenvectors corresponding to each of the 5 eigenvalues or 5 complex conjugate eigenvalues. Now, eigenvalues of the system matrix A can be easily obtained using MATLAB software, and similarly we can find out the eigenvectors corresponding to each of the eigenvalues. Now, these are obtained for the system which we have investigated. Now, here in this table I have shown the eigenvector. This eigenvector is associated with eigenvalue zero plus minus 20.21 I. That is, for this first eigenvalue I have obtained using the MATLAB software the eigenvector, and this eigenvector has 10 actually entries. Or now we can easily see here actually these first two elements of the eigenvector are associated with the rotor of generator, that is delta omega 1 and delta 1. Similarly, the next two eigenvalues, or not eigenvalues, next two entries are associated with the state variables associated with LP B rotor section, and so on. Now, here what we have done is we can consider the either the elements associated with speed or angle for analyzing the mode shape. Therefore, we have considered the elements associated with speed, not speed, but the angular position. They are the angular positions. Okay. Now, next we have plotted the magnitude of these elements. The magnitude is same as the 0.4346 because its real part is 0, and the angles are also shown. The angulars, for example, the angle associated with this element is 90 degrees, angle associated with this is also 90, angle associated with this is also 90, and so on. That is, all these elements have phase angle equal to 90 degrees. Now, when we plot the magnitudes of these eigenvector elements, right, what we will do is that those magnitudes which are positive, right, we will plot actually in the as positive, and those which are negative will plot in the as negative. Now, in this case we find that all the elements have the same angular position, and therefore, they are all positive. Now, this diagram shows the plot of mode 0. This mode 0 is the system mode whose frequency is 1.67 hertz, and this mode 0 has the magnitudes 1, 0.996, 0.993, 0.992 and 0.958. That is more or less all the state variables associated with this mode have the same displacement. Okay. And this mode, this 0th mode or system mode, represents that all the masses rotate together with respect to the system, okay, or rotors of other masses. Now, the next we consider the torsional mode. The frequency, the eigenvalue of the second or the first torsional mode is 102 plus minus 102.89 I, and its frequency is 16.37. Now, following the same approach, for this eigenvalue the eigenvector is obtained. Now, this eigenvector you can see here, it has again the 10 elements, and you have real imaginary and so on. Now, these elements are associated with angular displacements delta delta 1, delta delta 2 and delta delta phi. The magnitude and phase angle of these elements are written here as 0.4178 minus 90 degrees, because minus is associated here like that. Then this vector is normalized. When we normalize it, the element of the vector which is maximum magnitude or highest value, right, we use this as 1, right, and rest are represented with respect to this as the base. Therefore, we find here that the normalized values of the elements associated with delta delta 1, delta delta 2 and so on are given like this. Now, here the angles are minus 90, minus 90, and then they change over to plus 90, plus 90 and plus 90. Therefore, now if I represent this as positive, they will become negative, right. Therefore, the plot which I have shown here for this is starting from minus 1, minus 0.7676, minus 0.32, that is, this is the mass 1, this is mass 2, mass 3, mass 4, mass 5, okay. And you show the magnitudes positive or negative, this is our 0 line, okay. Therefore, this shows where we join all these points by a straight line, and this gives us a mode shape corresponding to the mode 1, or this is the mode shape of mode 1, whose natural frequency of oscillation is 16.3 hertz. Now, let us understand what we mean by this mode shape. The meaning is can be easily understood here, that if you look at this diagram, right, then the displacement of these masses 4 and 5 with respect to displacement of mass 1, 2 and 3 are in opposite direction. It means here the mass, there is generator, the rotor of LP A and LP B sections oscillate with respect to the rotors of IP and HP sections. That is, whenever the generator rotor is perturbed, right, and the torsional with this torsional frequency or with this frequency 16.3 hertz, in that case the generator, the LP B, LP A and LP B, they will oscillate with respect to the other two masses. And in this mode 1, there is one crossing, one changeover of sign, that is, you can just see here, actually this is a 0 line and there is one crossing here. Now, similarly, we have obtained the eigenvector for the mode 2. This is mode 0, we will call it mode 0, this is mode 1, this is mode 2. That is the frequency of oscillations or torsional oscillations, torsional frequency is 24.123 and the corresponding eigenvector is shown here. Now, if you follow the same procedure as we have done for other two cases, then we obtain actually the magnitude of the elements associated with delta delta 1, delta delta 2, delta delta phi. These are the magnitudes and these are the associated phase angles. You can easily say that the phase angle of this is 90 degrees, phase angle of these two elements minus 90, minus 90, phase angle of other these two again plus 90, plus 90. It means when we plot the magnitudes of these displacements, right, you will find that there will be two crossings, right, and the mode shape is shown here. There is this is the frequency 24.1 hertz and the mode shape you can see is like this. Therefore, there are two crossings here, that is, the mode shape will always have two crossings. Okay. Now, in this, when you try to analyze here, then you can easily understand that these two masses 1 and 2, these masses will oscillate with respect to the masses 3 and 4, and similarly the 3 and 4 will oscillate with respect to mass 5. That is, whenever it is disturbed or perturbed with the frequency corresponding to this 24.1, right, the shaft will oscillate in such a fashion, so that the mass 5 will oscillate with respect to 3 and 4, and 3 and 4 will oscillate with respect to 1 and 2, right, and frequency of oscillation is so much. Similar study is performed for the mode 3, whose frequency is 30.25 hertz, and this is the Eigen vector. Again we are considering the elements corresponding to angular displacements. Now, these are the normalized magnitudes of the elements associated with the speed deviations, and you can easily see here actually that we have 3 changeovers, that is start from positive, go to negative, then again positive and again negative, and this shows the mode shape associated with the mode 3, whose frequency is 30.3 hertz. And again now we can easily see here that when the system is perturbed, we will find actually that the mass 1 will oscillate with respect to mass 2 and 3, and 2 and 3 will oscillate with respect to mass 4, and 4 will oscillate with respect to mass 5, and so on, right. Similarly, the mode shape for mass 4 is shown, and you can easily see that there are 4 crossings. Now, with this, let me just summarize that we have studied the modeling of turbine generator shaft system. We have obtained the nonlinear and linear models, and we have also studied the application of Eigen vector concept to study the mode shapes of the system. Thank you.